Hello class, welcome to our next lesson here on related rates. And one of the nicest ways to actually see it is with an example. So I have here, suppose that x and y are both functions of t, which can be considered to represent time, and that x and y are related by the equation x times y squared plus y is equal to x squared plus 18. And suppose further that when x is 2 and y is 3, the derivative of x with respect to t is 13. We want to find the value of the derivative of y with respect to t at that moment. So from the equation, we need to differentiate both sides with respect to t, assuming x and y are both functions of t. Um, so for this, we are going to get y squared times the derivative of y with respect to t plus as a derivative of x with respect to t, plus um, 2xy times the derivative of y with respect to t, plus the derivative of y with respect to t, is equal to 2 times x times the derivative of x with respect to t. So, from this problem, we are told x is 2, y is 3, derivative of x with respect to t is 13. So, popping all of those in here, we are going to get 3 squared times that derivative of x with respect to t plus 2 times 2 times 3 times the derivative of y with respect to t plus the derivative of y with respect to t is equal to 2 times 2 times 13. And this derivative of x with respect to t here is supposed to be 13 too. There we go. So 3 squared times 13 plus 2 times 2 times 3 times the derivative of y with respect to t plus the derivative of y with respect to t is equal to 2 times 2 times 13. So 3 squared times 13, that made a value of 117 plus 2 times 2 times 3, that made 12 times the derivative of y with respect to t plus the derivative of y with respect to t is equal to 2 times 2 times 13. That made a value of 52. So if we subtract over the 117, that makes 2 times the derivative of y with respect to t plus the derivative of y with respect to t is equal to 52 minus 114. And that is going to give us negative 65. We can combine the two terms with the derivative of y with respect to t in them. So that makes 13 times the derivative of y with respect to t is equal to negative 65. And dividing by that 13, yes, gives us that value for the derivative of y with respect to t. And that is going to give us a value of negative 5 based on this problem. And here's a second example, yes? Small rock is dropped in a lake with circular ripples spread over the surface of this water, with the radius of each circle increasing at the rate of 3/2 feet per second. We're going to find the rate of change of the area inside the circle formed by a ripple at the instant the radius is 4 feet. So this uses the area of a circle. So area is equal to pi r squared. And if we differentiate both sides of this with respect to t, this is the derivative of a with respect to t is equal to 2 pi r times the derivative of r with respect to t. And in here, we are told radius is 4, and the radius is changing with respect to time at 3/2 feet per second, yeah? So this is going to become, let me write that up here. The derivative of a with respect to t is 2 times pi times 4 times 3 halves. So that is going to make 6 times 2, this is 12 pi. And as a decimal, 12 pi is about 37.7. So to answer this complete question, this would be the area of the ripple increases because it's positive by 37.7. This is going to be square feet per second. So from what these two problems should be showing us is that we first need to identify all given quantities, right? So these are the quantities to be found, what we're actually given, maybe draw a sketch if it's helpful. Write an equation relating the variables of the problem, using this implicit differentiation to find the derivative of both sides of this equation with respect to time, and applying the chain rule to further put all those values into the problem. And then solve for the derivative, given the unknown rate of change, and substitute the given values. So another problem, yes. 50-foot ladder is placed against a large building. The base of this ladder is resting on an oil spill for some reason, and it slips at a rate of 3 feet per minute. We want to find the rate of change of the height of the top of the ladder above the ground at the instant when the base of the ladder is 30 feet from the base of the building. So what does this mean graphically? This hypotenuse would be that 15 feet. We know this leg down here would be 13 for that length. Um, sorry, this is supposed to be 50 and 30. 50 feet is the length of the ladder, and 30 feet is how far away it is from the base of the building. And since this is resting on an oil spill, the ladder is being dragged to the right in a positive direction, which also means this ladder is falling down. So whatever that rate of change is should probably be negative in that sense, yes. To find that third side, Pythagorean theorem. 30 squared plus y squared is equal to 50 squared. So solving that should give us a value for y to be 40. So using the Pythagorean theorem without the 30 in it makes this x squared plus y squared is equal to 50 squared. And we're going to differentiate both sides of this with respect to t. So 2x dx dt plus 2y dy dt is equal to 0. And for this one, we could plug in the 30 for x, 40 for y, 3 for that change in x with respect to time. So this is going to be 2 times 30 times 3 plus 2 times 40 times the derivative of y with respect to t is equal to 0. So 2 times 30 times 3, this makes 180 plus 80 times dy dt is equal to 0. And solving for that dy dt, that is going to make negative 180 over 80. And that should give us negative 2.25 as the value of that when we pop it into a calculator. So what does that mean? This means that the ladder falls down the building, the side of the building, I should say, This would be 2.25, and the unit for this would be feet per minute. And then the last one from this, I have a cone-shaped icicle is dripping from the roof. The radius of this icicle is decreasing at a rate of 0.2 centimeters per hour, while the length is increasing at a rate of 0.8 centimeters per hour. And if the icicle is currently 4 centimeters in radius, 20 centimeters long, is the volume of this icicle increasing or decreasing, and at what rate? So it uses the volume of a cone, right? So 1/3 times pi r squared times h. Taking the derivative with respect to t to both sides of this. This is going to make 2/3 pi rh times dr dt plus 1/3 pi r squared dh dt. And then this one, right? We have radius of 4, height or length of 20, a change in radius to be decreased in 0.2, and a change of length or height being an increase in 0.8. So plopping all that in, which I'll write down here, this would be the derivative of v with respect to t. This is 2/3 times pi times 4 times 20 times negative 0.2 because of that decreasing, plus 1/3 times pi times the radius of 4 squared, and the height is increasing at 0.8. So, if we were to plop this entire expression into a calculator, we are going to get for that change in volume to be about 20, negative 20, slightly. This is going to be then the volume of the icicle is decreasing 20, this would be cubic centimeters per hour. So let me know if you have any questions or concerns. Thank you.